how does technology actually drive economic growth? It's a huge question, right? In this explainer, we're going to break down how economists have tried to model this incredibly powerful force and what their different approaches can tell us. So let's dive right in. All right, so here's our game plan. We'll kick things off with the basic role of technology, then we'll look at two classic models from economists Hicks and Herod. After that, we'll explore what happens when progress isn't so neutral, and we'll wrap up with a really interesting modern debate on where technology actually comes from. So let's start at the very beginning with the most fundamental question of them all. First things first, you hear economists throw around this term technical change all the time. But what does it actually mean? Well, simply put, it's a shift in the production function. You can think of that as the economy's recipe for turning ingredients like capital and labor into finished goods. So technical change just means finding a better recipe. You can get more output from the same amount of inputs, or hey, the same output with fewer inputs. The key takeaway here, it's all about a massive boost in efficiency. Now let's look at the first major model we're going to cover, which was developed by Sir John Hicks. His whole approach was laser-focused on the inputs themselves, capital and labor. According to Hicks, a technical change is neutral if it doesn't play favorites. It doesn't help out capital more than it helps out labor, or the other way around. It gives them both an equal boost. This means the ratio of their marginal products, that's just a fancy way of saying the extra kick you get from one more machine versus one more worker, that ratio stays the same, even as the whole operation gets more productive. And what's really cool is how this looks on a graph. The entire production curve shifts up, from OP to OP1. That just means we're getting more stuff done. But notice that tangent line coming from point M. The slope of that line represents the balance between capital's productivity and labor's productivity. And since it hits both curves just right, it shows that the balance between them hasn't changed at all. So the big takeaways from this graph are pretty clear. The mix of capital and labor stays the same, but the whole production function has leveled up. And the result? A clear increase in output for every worker, which you can see in that gap AB. That, right there, is a Hicks neutral change in action. Next up, we've got the model from another economist, Roy Herod. Now, he looked at the very same problem, but from a totally different angle. For him, it was all about the rate of profit. For Herod, a technology is neutral if, at a steady rate of profit, the capital-output ratio also stays constant. In other words, as long as the profitability of your investments is stable, the amount of capital you need to produce, say, $1 worth of goods doesn't change. And this graph shows it perfectly. Once again, production shifts up from OP to OP1. But look at that straight line, OR, shooting out from the origin. It passes right through point A on the old curve and point B on the new one. This tells us that at both of those points, the ratio of capital to output is exactly the same. And if you look really closely, you'll see the tangent lines at points A and B are parallel. What does that mean? It signifies a constant rate of profit. So this is a perfect Herod neutral change. The amazing result is that both wages and profits get to rise in direct proportion to that awesome increase in output. But let's be real, progress isn't always so neat and neutral, right? Sometimes technology clearly favors one thing over another. So what happens when technical change actually takes sides? Well, this leads us to two types of biased progress. Innovations that are labor-saving on the one hand, and innovations that are capital-saving on the other. In simple terms, a labor-saving innovation makes a machine more productive than a person. Think of a new robot on an assembly line that can do the work of 10 people. That's a classic example. And on the flip side, a capital-saving innovation does the exact opposite, letting you get the same job done with fewer or cheaper machines. Okay, this brings us to a really fascinating, more modern debate. Where does all this new technology actually live? Is it just an idea floating in the air, or is it physically built into all the new gadgets we buy? So there are two main schools of thought here. Disembodied technical change is like an idea, an invisible force, maybe a better way to manage a team or organize a factory floor. Think of it like a software update that magically makes your old computer run faster. But embodied change, that's different. That's built right into the new machines, like a brand new super efficient engine. Let's look at disembodied change first. This is a kind of change that boosts the productivity of everything, all at once, both old and new. The invention of the assembly line is the perfect example. It didn't just help new factories, it made existing workers and existing machines way more productive, practically overnight. And just how big of an impact can this have? Well, get this. In a landmark study back in 1957, the economist Robert Solow found that a staggering 87.5% of U.S. economic growth between 1909 and 1949 came from this disembodied technical change, not just from building more factories. I mean, that was a jaw-dropping result that completely changed how economists thought about growth. So, graphically, a disembodied change literally just lifts the entire production function upwards. The crucial point here is that for the exact same amount of capital and labor you had before, you can now produce way more output. It's like even your old machines got a secret upgrade. Now, in contrast to that, embodied change argues that new tech actually arrives inside new machines. This is sometimes called the vintage approach, which is a cool name. Each new model, or vintage, of a machine is just flat out better than the last one. I mean, a computer from 1980 and a computer from today are both capital, right? But there's an entire universe of difference in what they can do. In this slide, this brilliantly illustrates the difference with a great analogy. Disembodied change is often called putty-putty. Think of a material that's always soft and flexible, something you can reshape anytime. But embodied change is called putty clay. You have choices when the capital is still like putty. You can decide what kind of factory to build, but once it's built, it hardens into clay. Its design and how many workers it needs is locked in. So let's connect all these theories to our world right now. Think about artificial intelligence. What do you think it is? Is it a disembodied change, like a software update that makes all our existing computer systems smarter? Or is it an embodied change, something that only really comes to life with new, super powerful computer chips and massive data centers? Or is it actually a bit of both? Definitely something worth thinking about.